question for you would just be, how much variability potential is there with this class of materials? And do you think that will lead to even a wider range of applications in the future in the next 10, 15 years?
I would say infinite, and it's not far-fetched. Because if you do the permutation combination of the existing elemental space in the periodic table, you can create a lot of possibilities and tune these compositions accordingly, and which will result into a change in structure, which will then engender different properties, which in turn can be used for different applications. Up till now, the focus is driven in terms of
Hello, everyone. Welcome to the It's a Material World podcast. I'm Puneet, and alongside me is David. And so for today's episode, we're diving into all things perovskites, which is a super interesting discussion topic, specifically for me, because it kind of brings me back to my research from freshman and sophomore year at Georgia Tech, where it was a battery research group with Dr. Gleb Yushin, but I focused on kind of a anti-perovskite material. I think it was lithium hydroxychloride, and how that can be potentially used in a battery application. And so that just kind of coincides with the topic of today's discussion, because we discussed the various applications of perovskite materials. It's a very interesting structure. Kind of Akash talks about the ABX3 structure, or the formula, and all the properties it enables, and therefore kind of the most well-known application is solar cells. So we have that discussion of, perovskite solar cells versus the current silicon solar cells, but then we also talk about a variety of other potential applications. So David, I wanted to see if any of those kind of were your favorite points of discussion, or what was a highlight for you?
Yeah, I really enjoyed talking about the scalability and application. And so in that, we already have the silicon solar cells, which we see throughout throughout our lives, the most common. But he really talked about how perovskites can be used in a different manner while still using silicon. So the combination of two technologies to meet a need. So in this way, they are much thinner than silicon cells, and they can be embedded as they are soluble. So it's much easier to laminate, embed in other materials to create combinations of infrastructure in these solar cells. So I just thought that was super interesting about how do we continue to scale to make this green energy even more accessible and more prevalent without taking up any more space, because we know that space is such a valuable thing. So I thought that was really interesting to hear how there's a lot of benefits of how thin it can be, like upwards of hundreds of nanometers. So very, very thin. And that could be used in our Apple Watches. It could use V-Power, those types of technologies. Because it's so thin, it could just be on the technology itself. And so I thought that was all very fascinating to hear about how we could still use both technologies, but they can meet different needs, and they can be used together as it will take a lot to be able to make something that can solve all of our problems with energy production in a clean manner. So that was my favorite part of the conversation.
And for me, it was really cool to see he was talking about the time frame, like the 60 to 70 years that silicon had to optimize its manufacturing process. And I believe they're around 26% in terms of their efficiency. And he just touched on how with the perovskite material class, it's jumped up from 3.8% to now 25.4% since just 2009, less than 15 years. So it's really cool to see that rapid innovation and progress being made in this class. And it seems like there's a lot of potential here that has yet to be uncovered. And another really interesting conversation we had was Akash is a Ph.D. candidate at Duke. And so he has a lot of experience with the publication process, not just writing, but also reviewing for various journals. So for any student, graduate student, undergrad student who's writing papers, we have a really good, where he just shares a lot of advice towards the end of the episode to look out for in terms of how do you get your message across and improve the quality of your scientific writing and the impact and make sure that you can publish papers as frequently as you'd like. So there's a lot that we talk about in this discussion. So without further ado, let's get into it. Hey everyone, welcome to the It's Material World podcast. So for this episode, I'm happy to introduce this week's guest, Akash Singh, a current fourth-year Ph.D. candidate at Duke University. Akash's research is centered around perovskite materials with the goal of enabling next-generation solar cells, sensors, memory, and computing devices. Akash received his bachelor's in mechanical engineering from the Indian Institute of Information Technology, Jabalpur, and conducted his undergraduate thesis work at the Indian Institute of Science, Bangalore, or IISc. After his bachelor's, he extended his research on perovskite materials for another year at IISc before joining the PhD program at Duke. Akash, thanks so much for joining us today. We're super excited for this discussion.
Well, thank you so much, Puneet and David, for having me here. It is such a pleasure and a big honor for me to be here on this platform. And kudos to you both for doing such an amazing job, surpassing 100th episode for this Materials World podcast. Congratulations on that. And I'm excited to be here.
Awesome. Well, yeah, welcome, Akash. It sounds like you're doing some big stuff in the space, but before we dive too deep in any specific innovation, could you quickly just describe what that class of material is and what makes them so desirable for solar cells?
Well, yeah, great question. Perovskite is a material that has in structure. It is characteristically known through in structure of chemical composition of ABX3, where A, B, X are different elements from the periodic table. And these minerals have been discovered in 1839 in Russia. And since then, there has been significant interest in these class of materials. More interest have been recently grabbed in this area after 1974, when these materials could be synthetically synthesized to get the best of the both worlds of the organics as well as inorganics, as well as the synergistic effects that engenders from the combination of these two. So these materials can be widely tuned because we can replace A, B, and X, which are the primary structure ingredients for these materials. And we have infinite space of choosing from all the 114 elements from our periodic table, which can give rise to different functionality in these materials. These materials tends to show some unique properties as compared to other semiconductor materials. And one of them is that these are solution processable. So we can just dissolve some salts, precursor salts, and can deposit it over any substrate using simple coating techniques like spray coating, spin coating, or even inkjet printing, so that these materials can be printed over a large area with a very high throughput. As well as these materials, as I told, it brings the best of the both worlds. So they tend to have a very unique behavior, which is known as defect tolerance. So for solar cell applications, most of the things that you see around in the market is based off silicon. And these are single crystalline silicon, which do not have grain boundaries, which are detrimental in its performance. In these materials, even if you have grain boundaries like polycrystalline material and not a single crystal wafer, these defects do not appear to degrade the performance of the devices that are made out of it. And so they can be easily processed. Third thing exciting about these materials is that silicon, which is used in solar cell, as much as abundant in the form of sand, it requires around 2000 degrees Celsius for its processing, and sometimes in the clean room environment, whereas these simple salts can be deposited with as less as 100 degrees Celsius of thermal energy input to get crystalline layers to work as a solar cell absorber. And and these are very thin materials. So you can imagine making solar cells out of 600 nanometer to 1 micron, whereas for silicon, you require around 600 to 900 times more material, because silicon is an indirect band gap. As much as we say silicon is a good solar cell, but it is not a good light absorber. So we require a thicker layer. Here we can do with few hundreds of nanometers. These things makes them interesting, apart from the other properties that are also used in other applications, which we can discuss later.
Sure. So I'm curious, you explained that the kind of the generic formula is ABX3. My understanding is, or I just wanted you to walk through what that structure looks like, from like the simple cell, or I guess what I remember is, that ABX3, it's kind of like there's a simple cell and then like a tetrahedron like in the middle of it, and then like a center atom. Can you just kind of walk through what the structure looks like for our audience, and then how that leads to the potential benefits from the property side and the performance side?
Yes. So for ABX3 is a three-dimensional framework of perovskites, though they can also be made in 2 dimension and 1 dimension, and that way their chemical formula will be different. But for the 3 dimensional aspect, A could be any mono cation. How do I say? Yeah, it's cation. And B is a divalent cation, and X is a halogen anion. And when these are mixed together, if they are in the perfect ratio, then the B and the X forms an octahedra. And these octahedras are connected in infinite space along XYZ direction. And when these octahedras are joined, it forms a cavity inside, wherein the A cation sits. And that leads to different configuration of these materials. And depending upon the angles of these arrangements, we can have different fundamental band gap of the material, which gives its characteristic colors, and as well as different properties depending upon what kind of cation or anion we are substituting in this perovskite moiety. Structure, earlier these minerals were called perovskites in the honor of Russian mineralogist Perovsky, who actually funded the crusade for the trip to Russia. But after World War II, when people formed synthetic perovskite and not the original ABX3, which was calcium titanium oxide, they found out that even if you replace these elements, the structure remained the same. And since then, it was no more the mineral which was named as perovskite, but the characteristic ABX3 structure.
So when we talk about solar cells, perhaps you could briefly talk about why this cavity and this ion in the middle is so preferable for solar cells. Just like very briefly, like the energy of the sun can knock it out, and then it will release energy as it finds another cavity. But maybe you could describe a little bit more about how this works to create like efficient solar cells, or at least solar cells that make like some amount of energy that's not negligible.
Yes, wonderful question. So it's the cavity that holds the structure. If you put something in it through charge neutrality, because everything in the space has to be charge neutral for it to exist, if not plasma. So it's not exactly the role of the cavity. The role of the cavity is to hold some atoms or a small molecule such that the structure could be held in its place. Regarding the other part of the question, which is why these are so desirable for photovoltaics, is because of 2 to 3 reasons. One, these are direct band gap materials. That means you do not require thick layers, as I mentioned previously, as opposed to silicon. So even very thin layers of the material can absorb more than 90% of the incoming solar radiation, because we want to maximize the absorption of the sunlight in the solar cell. Now, the second point is the defect tolerance. Even if these semiconductors absorb the light, which they then create electron and hole pairs, which we isolate and conduct through external circuit, which produces the current, which we then use for our day-to-day application. In these semiconductors, these electron and hole pairs that are created, they are quite mobile. They do not get lost due to recombination. Before they can recombine non-radiatively, they can be extracted easily through an external circuit, such that whatever photon created electron hole pair, we tends to get around 90 to 100% of the things that are created. So there's a term in solar cell physics called external quantum efficiency. So for these materials, the quantum efficiency is very high, even if the material deposited is not very uniform, like I talked about grain boundaries. And the third point is, again, related to the grain boundaries. They are very defect tolerant. Generally, suppose if in any crystal, a particular atom is missing, that will create a void, and some electrons and holes can get trapped in those states. Whereas in these perovskite materials, those trapped states do not come in the band gap of the material. They either exist within the valence band or in the conduction band that forms the band of the material, which gives their respective colors. Like suppose a material is black, so it has smaller band gap. A material is orange, it has bit higher band gap. And if a material is transparent, it has even higher band gap. So we ideally want black color. So that means we want the band gap to be low. So even if the band gap is low in these materials and there are some defects, these defects are not detrimental in the conduction pathway of these photo-generated charge carriers, and we can easily extract them out such that we can get efficient solar cells.
I think we'll dive into solar cells and the comparison with other kind of current technologies later in the episode, but for now, I wanted to discuss some of the work that your lab is doing. I know that your lab is exploring glass-forming perovskites versus the traditional crystalline form. So just wanted to get your thoughts and just what exactly makes a glassy perovskite special and unique compared to the traditional crystalline form?
Thank you for asking something that I'm currently doing. So it's very fresh to my knowledge. So before we delve into like why it is special, I would just like to define this term glassy. When we think about glass, we tend to look up at the buildings or the windows for our buildings and we see, okay, this is glass. Well, glass is actually another metastable state of matter, the way at least I look at it. So we can imagine that in a crystalline materials, all the atoms are periodically repeated. And if you heat this crystalline material beyond a certain point known as the melting temperature, then it forms a liquid. And then when the liquid is cooled, it goes back to its crystalline form. The atoms move back to its home position. Now, suppose if you have melted a material and then it is in the liquid state and you cool it in such a super fast manner that the atoms in the liquid do not get enough time to go back to their parent home position. That leads to the creation of a metastable state that we know as glass. Now, this metastable state glass is not a thermodynamically stable phase, but is still stable in the experimental time scale of our observation. And this glass has a structure which is similar to liquid, but physically it is quite similar to a solid. And this gives rise to multiple configuration arrangement as opposed to a very few available for the crystalline counterpart, and which engenders multiple functionality. Like in glassy materials, you do not have grain boundaries that are known to be detrimental for the application of solar cells, wherein the attacking molecules, the oxygen and the moisture, permeates through inside the bulk and degrades the active absorber layer. In the glass, you do not have them, so you can make even more stable material or even as a barrier coating. The second thing, if you can make these materials in the glassy form, then you can think about drawing optical fibers out of it, which can be used in communication like transatlantic and transpacific communication without the requirement of multiple repeaters that we generally use currently. The third part is that when very high efficient devices have to be made, there is a term known as epitaxy, when one layer has to be in very intimate contact and all the atoms has to be in intimate contact without any dislocations. Glass are insensitive to these dislocations and grain boundaries, so you can have a perfect match when you make in heterostructures. Other than that, they also have lower thermal conductivity, so you can envision using these materials as thermal barrier coating as opposed to crystalline materials, and a multiple application as well. Like one of the interesting one that I am trying to work on is you can also switch these materials from glassy to crystalline, and these two states shows different optoelectronic properties. And when you have two different properties within the single material that can be altered using some external stimuli like electric current, like photo exposure, or even like thermal stimuli, then you can have two different states, and then you can think of switching between these states. So you have a switch which can potentially be used as a memory or for neuromorphic computing devices, which was not much earlier accessible when we only talked about the crystalline state.
Interesting. So I'm just curious then, with the glassy state, you were talking about how it's kind of in a metastable nature, doesn't go exactly to that repeated pattern. Does that change like when you're talking about the structure itself of like, the octahedron, for instance, the octahedra, does that change at all with the glassy perovskite? And how does that affect its property or performance?
That's a great question, actually. So we have been investigating it over the last 2 years, and one of the experiment that I did at Oregon National Lab was with a beamline experiments. We also call it a particle accelerator, just a fancy term for that. So using that, we probed into the structure of these molten and glassy materials, and we found out that the repetition of the octahedra in the infinite space is somewhat constricted, but they still maintain that octahedra, though they connect loosely with one or two. So you can consider one octahedra as a monomer unit, or if two octahedras are connected, then it's a dimer unit. And up till this point, we have come to this conclusion that the connectivity has been reduced when it forms a glassy, when it exists in the glassy phase, but it still maintains its octahedra nature, and that's why some of the properties are still preserved, but distinct from the crystalline counterpart. Like it shows different absorption spectra, as well as it shows a two-order change in electrical conductivity. So when I say switch, so you can think of making even compact discs or DVD, Blu-ray devices that we generally use in our old computers. I don't think so. We use CDs, DVDs more because the SSDs are based on MOSFETs now. But if it can be electrically driven, that Intel Optane was launched in 2019, which used a chalcogenide-based phase change memory device, which was electrically driven. These materials can also be envisioned to be used in that due to the change in property as a result of the change in the connectivity of these octahedra, which is the structure change.
You talk about all this progress, and there's been a huge jump of research in perovskites specifically recently. What specifically do you think is driving such interest in this new field of material?
One is climate change. And second, there is a great push from the government as well as different organizations to reduce the carbon footprint, as well as develop alternative technologies, alternative renewable technologies, such that we can minimize our reliance on the fossil fuels. And one of the great impetus is that. The second one, the accelerated materials discovery, even using the artificial intelligence and the wide scope availability of the literature because of the internet. And so if you see from silicon solar cell were made in, if I'm not wrong, maybe Bell Labs, and it took around 60, 70 years to come up to this point with efficiency of around 26% in the lab. With perovskite, it was 3.8% in 2009, and now it has reached around 25.4 in just a span of 15 years. So a lot of people have started to research. A lot of information is available on the internet. A lot of new technologies has come into existence, including fabrication, synthesis, as well as characterization techniques. And a major impetus is definitely the government and the organization, and towards the common goal of making a carbon-free world in the future. These are the things. And also, these are very interesting class of materials because they have both organic and inorganic. So from a curiosity point of view, people want to study these hybrid systems. That has led to the observation of some properties that ultimately found its application in these fields.
It's awesome. I know one of the patterns we've seen in our episodes is there's an existing technology that's had decades and decades of, just being able to optimize the manufacturing process. And then there's a new technology that is very much in the early stages, but there's a lot of potential for it. And it seems to be the case here. So I was wondering if you can kind of talk us through that comparison between perovskite-based solar cells, for example, or products in general versus like the silicon solar cells. You talked about the efficiency currently, I believe you said 26% versus 25.4% as it is today. What about like the cost differences or manufacturability and scalability for perovskites versus silicon solar cells?
Yeah, so regarding so there are 3 points. For the cost, there is something known as levelized cost of energy, and which is a normalized way of understanding what is the end result, like how much energy are we producing at the expense of the dollars that we are spending on it. So if I can remember correctly, and if my numbers are good, I think for the silicon, it was around 35 cents per watt. For the perovskite, it is around 17 cents per watt, but it is envisioned to go as low as 7 cents per watt. And regarding the manufacturability of these materials, so as I said, these are solution processable. So you can imagine having a spray can and just spraying it over a window, putting some, like electrodes or wire in the future. Also, like I have been working on this spray coating projects in my undergrad, and it showed success to a good extent. So as I also mentioned previously, that you can print these materials with the speed of newspapers. And the speed with which newspapers are printed and the area on which it is printed. So there is definitely a benefit on that. The climate, the change regarding the climate, the footprint that silicon takes to produce and the ecotoxicity is quite high because of the thermal requirement, 2000 degrees Celsius, as opposed to these solution process materials, which requires as less than as 100 degrees C. Some reports have even developed these materials to be deposited at room temperature in 2017. And the third part, what was the third part actually?
Scalability, really just being able, how frequently are silicon solar cells, to what scale are they made versus perovskite, and kind of what that potential looks like. I know it's early stage.
So for the silicon solar cells, we generally tend to make an ignot, a big cylindrical single crystal, and then we slice those single crystals in different segments with a cross section of around few hundred microns to a millimeter, and then those different wafers are connected with each other with different layers on it to make a panel. With perovskite, you can have a monolithic integration that doesn't require you making individual cells and connecting them to form a module. You can have one complete surface covered by it, and you can make solar cells out of it. And if you think about perovskite, there is an anecdote told by Sam Stranks from University of Cambridge. You imagine a Olympic-sized swimming pool, and you use the precursor ink like solution processable, because these are solution processable materials, and you barely fill half of that swimming pool. And the ink that is there, it can coat, if you coat it over substrate, it can power all of California. So there is a very high potential and throughput for these materials compared to silicon, while being done at a very fast pace.
So how easy is it to combine and almost like embed in other things? Like you said, like you can make it solution soluble, but how compatible is it if we want to put it on glass or other substrates that we use for buildings, or combine it with other technologies that we already have? Is it very easy to combine it with infrastructure to be able to take advantage of things that are in the sun all day? Or it'll have to be like a standalone, like a solar panel, where you do have to have some infrastructure specifically just to hold it?
That's a great point. And a lot of work has currently been done in this regard, especially related to tandem solar cells. But you can think of them as a standalone technique as well, because these are thin materials, so you can envision printing them over a flexible substrate, so that you can roll these devices and can spread it out open in the sun and can harness the energy. So you can think of this as a standalone flexible solar cell technology as well. But other thing regarding the compatibility, because these are hybrid materials, so it's easier for them to stick to an organic surface as well as to an inorganic surface. And there have been reports of these coatings being developed on almost all the surface, including surfactant bubble that was shown a few years back. So I don't think so there are any compatibility issue with its coating on different surface. And if there are different surface enrichment techniques that can change the surface energy of the substrate, and then you can coat even philic or phobic materials on those substrates. Regarding tandem, if you think about the existing infrastructure, silicon solar cells are already existing in the market, and there have been a great impetus of using perovskite as an additional solar coating, a wide bandgap solar coating on these materials, using the existing infrastructure at a fraction of cost to extract even more energy out of it. Like, I think the recent record is around 32%, as opposed to a single junction solar cell for silicon, which is 26. So, and Oxford PV is a big player in this market that is currently trying to do that. So yes, I can see them existing as a standalone technology as well as quite integrable with the existing infrastructure. Also in IoT devices, the small, because these are highly efficient materials, and very light. So you can imagine your smartwatch or any wearables being powered by that, even in ambient lighting conditions.
So it seems that solar cells take a lot of the interest and the attention-grabbing applications of perovskites, especially the push for green energy and other products as we try to combat climate change. However, after talking to you, it seems like this might overshadow some other exciting applications of this material class. Maybe you can dive into what other applications we can use these for and what excites you the most out of these.
What excites me the most is just working with them, honestly, because the curiosity and the fundamental properties, investigating those fundamental properties and relating it with the structure takes the biscuit for me. But there are multiple other applications that these materials are used in, and I think in mostly all of the application fields. As you know, for a semiconductor, a good absorber is also a good emitter. So LED devices are currently being made out of these materials, which silicon cannot be used because it cannot emit light, because it is an indirect material, whereas these materials are direct, so it can emit photons instead of just heat. And because these are widely tunable, so you can tune their band gap all the way from infrared to UV. So you can imagine having all different color gamuts from compositionally tuned perovskite films. So you can have green LEDs, blue LEDs, red LEDs, infrared LEDs, or UV LEDs made out of that. Apart from that, these are also used as sensors. One of the most exciting applications is its use in detection of X-rays and gamma rays. And that is currently taking a lot of interest in the perovskite community. And people have also made transistors out of it, diodes out of it, lasers out of it. And with the advent of this glassy materials, glassy perovskite, I envision that their application space will be broadened to an extent where these can be efficiently incorporated or perhaps be individually used as in a standalone format as memory devices, neuromorphic computing devices, metamaterials, photonic devices, because the very fundamental property of the switching between glassy and crystalline opens many doors of possibility for these materials. And since its discovery in 1839 up till now, a lot has been done, though a big progress has been made in the last 15 years. In the next 15 years, this mineral will complete its two-century journey, and I think that it's a very bright future for this family of materials.
Fascinating. It's interesting to see how the variability in like the structure affects its potential applications. You mentioned like the switch, and this is, way back in freshman year, but I worked with like anti-perovskite materials, which I guess is like X3BA instead of ABX3, something like that. But it was like a lithium-based anti-perovskite material for battery applications. And so the question for you would just be, how much variability potential is there with this class of materials? And do you think that will lead to even a wider range of applications in the future, in the next 10, 15 years?
I would say infinite, and it's not far-fetched, because if you do the permutation and combination of the existing elemental space in the periodic table, you can create a lot of possibilities and tune these compositions accordingly, and which will result into a change in structure, which will then engender different properties, which in turn can be used for different applications. Up till now, the focus is driven in terms of solar cells, emitters, and sensors. But as we discovered the glassy perovskite out of a mere serendipity, we were trying to measure the photoluminescence of these materials and their melting properties. And when we actually melted it, it never recrystallized. Before, we did not know that it even exists, and there could be switching phenomena that could occur in these materials, which just happened like 2 years back. So there is still a ground of new possibilities. We are just still waiting for some of those discoveries to be made. And given the memorphic tunability and compositional space to choose from, I think there are still a few strides for this material to make its mark into. Like earlier, if you talk about semiconductors to exist, you need a crystalline framework. In 1968, Stanford Arov-Sinsky demonstrated that semiconductor nature can still exist in the material, even there is no periodicity, which also in part led to a Nobel Prize in 1970s. And so for these perovskite, it was the structure. So when a material is defined by structure, that means it's crystalline. mostly. So there was no possibility even for it to be understood to exist in a glassy framework. But now it is. So you never know. As more people like us start to work in the material science, we would definitely see more progress in this domain, and which also encourages me to talk about these two people in material science community.
Sure. That's why I wanted to ask you about what you first see, like in terms of timelines for like mass scale, let's say commercialization of perovskite solar cells and the implementation. What are like the current companies working on today, and what does that timeline look like to see this? Because it seems like there's a lot of potential applications, but we're not quite there yet in terms of, I guess, mass scale production, right? With this perovskite material. So I just wanted to get your opinion on what the future looks like for the space in the next 5 to 10 years.
So currently we have around new startups are growing, and around all over the world there are around 90 startups, with around 29 in America, as well as 2 in my home country back in India. And these involves not only those which work with perovskite solar cell fabrication, but also involve the ones that provides materials for its production, provide services for its production, as well as the one that develops the panel, the ones that provide equipments for them to be produced, and as well as other sectors which work on exploring different applications apart from the photovoltaics. Currently, there are few big players to name, like Oxford PV, Cubic PV, Sol Technologies, Bus Solars, Great Cell Solar, that are there and contribute to the most market share currently in all over the globe. So according to an analysis done by DataBridge in 2020 or 2021, it was estimated around $0.17 billion market in 2021 and is projected to go to around $6.6 billion by 2029. And the reason we are not able to see these solar panels in the market, no matter how much I incentivize or talk good about these materials, is because they are still in that development state. But a lot of solar panels have come out recently. Even last week, I read there is a panel of 2 meter by 1 meter of 320 watt capacity that came out, I think, from an East Asian country. And different companies that I mentioned, those players are also working towards it. So I expect us to see these solar cells in the market within the next 5 years, most definitely. Not being optimistic, but most definitely. And as well as in space, which they are currently being researched in.
Well, yeah, maybe taking a slight detour from your very technical side, we just wanted to ask you about how you founded Duke University's Materials Research Society chapter, MRS. We touched on this several episodes ago, but could you briefly describe what MRS is, and then why you saw the need to create this organization, and what made you interested in spending even more time doing things at Duke?
Well, Duke is a great place, and especially its material science program is a bit unconventional, I feel, in my own personal opinion. Rather than having a dedicated department of material science, they have a university program in material science and engineering that takes students from all the 9 departments at Duke, including the natural sciences as well as engineering and environment. So people working in all these respective departments can be affiliated with the university program in material science to continue their research, because materials is ubiquitous. No matter whichever field you go, you have to deal with these tangible matter at hand. And there is a body of the professors here at Duke called Duke Materials Initiative, which currently includes around 62 professors from these 9 departments. But there was no such organization that was student-driven. And there was a gap between the communication between the faculty-led organization and the student-led organization. So during the COVID times, there was not much to do socially. So I and the DGS, Professor Adrian Stiff-Robert, amazing professor and the director of graduate studies program in material science, we talked about it, and there was also a push from the department to create such a organization, and we talked about it, and I started recruiting members because I felt there is a disconnect between the students, and there could be better discussion between the faculty as well as the students across these 9 different departments, and there would be interdisciplinary as well as multidisciplinary discussion that would be engendered through it. So we formed it, talked to the headquarter, and initially people were interested in it. Currently, we have around 160 members across the Duke campus, and hopefully we'll grow more.
That's so awesome. It's interesting. It just resonated with me when you were talking about like the COVID times, not much else to do. Like that was a similar story with this podcast. So I'm glad that the MRS chapter at Duke is continuing to grow, and it seems like you really enjoy your time there. My little brother goes to Duke, so yeah,
great.
and I'm from North Carolina, so it's good to hear that you're enjoying it, because that means that there's a good chance he'll enjoy it too. But I wanted to first of all thank you for this discussion and really wrap up with getting your advice on something that I think you have unique experience in. So, like as a PhD student, we want to talk on the publication process specifically. So we've seen that you authored several papers. You're the first author on multiple research papers, but I believe you're also a reviewer for a variety of journals. So since you see both sides of the publishing process, what advice would you give to students who want to improve the quality and impact of their scientific writing?
So I think there are a few points that can be kept in mind. One, when you want to write about something, that means you want to do two things. One, to enhance the repository of the knowledge in the scientific community, and second, to communicate it better so that it is readily available to other people as well. When you want to write a journal paper, one should always keep in mind what is the punchline, what is the main message that you want to deliver, the major findings. One, as long as you stick with it, it's great. The second point is sometimes we get lost in doing experiments that we deviate from the major focus, and it gets hard for people to, like wrap up the work and to communicate it to a point where it is itself self-existing in its own. So I would say not to overkill. If something is not working, we have to quickly move into different ways of figuring it out together so that it can be written quickly and communicated. Third thing is people tend to be very liberal with writing. So they, including myself, I'm talking about me. So I would just write few lines which are not backed up by which are just hypotheses and are not backed up by references or scientific concepts or the experimental evidence. So I tend to now avoid writing anything which does not gives a clear-cut message, because as a reviewer also I find that when you write something and which is not backed up, then you invite more questions from the reviewers, which make the reviewing process more difficult as well as more time consuming, so that your communication is not communicated in a timely fashion. That's the other thing. And if you really want to write and communicate fast, I think you should have a set of figures in your mind. So envision them here. What are the figures that you want to do, and chart your story around it while keeping the punchline and the major message, your paper, in your mind, and just navigate through it, create a good flow of logic rather than having jumpy paragraphs. I have struggled about it, and I'm still in the learning phase, but these are I find out that has helped me publish whatever I have published so far.
I love that. Well, thank you so much, Akash, for joining us for this discussion and sharing all the valuable advice you have, as well as an overview of the perovskite space. I'm excited to see this field continue to grow, and I just wanted to express that gratitude and appreciation for you sharing all of your insights with us today. Really appreciate it.
The pleasure is all mine, Puneet and David. I feel more honored to be here in this podcast series. I think it is one of a kind.
Thank you.
Very delightful to share my views about this technology, as well as getting a chance to talk to you both, who have definitely knowledge about all the different kind of material segments, since you have been doing it. And I think it's more than 100 episodes. So thank you so much for having me here, and I wish to continue to have further conversation and communication in the near future.
As a materials engineer, we can make an impact in nearly every single industry. But with that versatility comes a lot of different options to choose from. So if you have no idea which industry or position is right for you, believe me, you're not alone. I've been there, done that. But just for a moment, imagine narrowing down your ideal role and company by the end of this week. Imagine being able to secure your dream job offer without having to apply to hundreds of job openings. Our online course, MSc Academy, includes video testimonials, resumes, interview prep, and mentorship from materials engineers who have been in your shoes. We also connect our members with companies and industry professionals in our expansive network to help accelerate your job search as much as possible. To learn more and get started, simply click the link in the description below. And if you enroll within the next 24 hours, we'll add 3 bonus career development resources. I hope to see you there.